Okay, guys, going over the questions 14, 15, and 16 theory. I'm going to start with the stuff that I have written down here, which is basically just slide 5.91, as I've stated, and some of the stuff from 5.92. Now, the first thing that you're going to notice is that u must be c to the m minus 1, which is what I have stated as my first requirement. What this means is, well, it's kind of defined as the patch element. So if we have a set of like a mesh, so we've got a couple nodes here that are all going to be connected in triangular fashion. Sorry, the drawing is rough, but you guys should get the idea. What it's saying is that on each element, since our shape function has to equal, if you remember from the linear version of this, the shape function has to equal our displacement UA at A, and it has to equal 0 at B. What this is telling us is that u right here must be in the order of c to the m minus 1. So if we have a second, like a second order polynomial, so m equals 2, I'm sorry, m would equal 1 in a second order polynomial, because the order of the polynomial is defined as 2m. What we have going here is that c is going to be the order of 0. This means that c is like a step function. So u must be equal to the value at point A at point A. It's a little bit confusing, but all that's really stating is the continuity that we've discussed in class, the fact that it must reach this value at point A. A little confusing. If you guys have questions, I'll explain it a little bit more at that time. Moving on to requirement 2, u must contain a polynomial of order m. So in this, remember back in the case of a second order beam problem, like an axial loaded beam, the order of the polynomial is going to be equal to 2m. So m is going to be equal to 1 in this case, and we notice that, as defined before, the shape function the shape function na of s, where s is our localized displacement here in the per element, is going to be equal, in this case, to ua times 1 minus s over little l, where little l is the length of the element. Now you'll notice this is linear, satisfying the fact that u must contain a polynomial of order m. Just as a reminder too, u tilde is defined as the local approximation of displacements. So that is what we are dealing with in this case, just so we don't forget. Okay, so this is clearly satisfied. It's a little bit more confusing when we move to the two-dimensional sense, but it should be fairly straightforward, as I explained yesterday. I'm not sure how many of you understood or saw my drawing. I'm going to do another little 3D guy going on here. Okay, so we've got this 3-node triangular element, and what we need to do is we need to draw linear shape functions for each one of the associated points. We're going to do, each one of them has a value, so we'll call this UC, and this is point C. UC is going to be a plane. Actually, you know what, let's draw that right here. It'll be a little easier to see. So UC will be this plane. You can all see that it's this plane right here. And if you can imagine that applied, if you move this guy so that C becomes A, and this one becomes this one, and this one becomes this one, you'll notice that this will correspond to the value UC at point A, which this is fine because this is the element level and this is like the global level. And you'll notice that since it does reach UC, it satisfies 1, and it's a linear function, because planes are just the 2D extension of a line, so it satisfies 2. And now we're going to move on and look at 3. U tilde must be able to represent constant mth derivative field as h tends to 0. Now, what h is defined as is the element spacing, which is a little bit confusing in 2 dimensions. But what we are going to be dealing with here is, good grief, computer's freaking out, sorry guys, is we're going to be dealing with the size of the elements. What all this really means is that if you'll notice, as we change L, the slope of this line is going to change, and we basically have to achieve at least an mth derivative as that goes down to 0. It's a little bit hard to explain. I wouldn't worry about this one overly much. If you give me a few minutes, I'll have a better explanation of it. And then this is the general explanation. I will go on to a more exact explanation of the specific cases listed in 14, 15, and 16 as soon as I possibly can.